Wow, I'm pretty impressed. Thank you everyone for joining today's webinar on long-range reader performance. I'm really pleased by the turnout. I hadn't anticipated a global turnout. Maybe I would have adjusted the time. So now I have to adjust my opening remarks. And so let me begin by first saying, good morning, Asia and Australia. Thanks for rising so early. And good evening to Europe. Thank you for giving up your evening. And good afternoon to the rest of us. My name is Mike Verbena. I'm the Executive Vice President of Feig Electronics, and I'm speaking from Feig's US office in Duluth, Georgia. Just to establish some credibility here to those unfamiliar with Feig. Feig is a privately held manufacturer headquartered in Weilburg, Germany. We're celebrating our 50th year anniversary. Yeah, we've been around quite a while, and we're an OEM manufacturer of RFID readers compliant to ISO standards defined for passive radio frequency identification. And that encompasses low frequency, high frequency, and UHF. Most of our production volume is embedded into clients' RFID-enabled products, so you probably won't see our name. And while we regularly talk to end users to understand needs and requirements, we don't sell to equipment to end users. Rather, we choose to exclusively distribute products through indirect channels of value-added resellers, system integrators, and OEMs. Last year, we shipped nearly 250,000 devices to the worldwide market through those channels. We've put together an informative session that I expect will last 30 minutes or so, but may cause so many questions it could last for hours. We won't have all that much time, but we purposely scheduled this presentation in advance of the RFID Journal live show, the largest RFID event in the world. It's going to be held in Phoenix, Arizona, the week after next. I think many of you will be attending the event, and we invite you to stop by our booth to talk to us should we not have an opportunity today to touch on a particular topic, a subject, or to answer a question. I see several friendly competitors in the audience too, obviously interested in what an industry peer may have to say. We welcome you. We're not taking any shots at anyone in this webinar, although Feig's marketing department wanted to call this a shootout. No one's going to get hurt here. We're just reporting relevant performance features observed in controlled conditions of similarly classed UHF products. Everyone in our industry makes a good reader, so relax. That's not the point of this, but I do think your eyes may be opened as well. This webinar is being recorded and will be posted to our YouTube channel for future reference. In addition, the presentation has been made into a white paper that can be downloaded from our RFID Reader News website. We'll show you that at the end of the presentation. Questions to us may be posed through the GoToWebinar control panel on your screen. Maybe familiarize yourself with that a little bit. We'll collect them up and answer as many as we can at the end of the presentation. Of course, based on the size of the audience, you're all muted. We don't hear your audio. I'm joined today by Klaus Schocke. Klaus is the Vice President of Technical Sales for Feig Electronics. And many of you that know Klaus will understand when I say he's the embodiment of an encyclopedia on the technology of RFID and RFID products from Feig Electronics. You would find him more often than not in an airport rather than in this office. If he's not meeting with a client or attending an industry trade show or speaking at a conference or doing a training seminar, you'll find him with a phone to his ear or in the early morning hours that he keeps when he says he gets more done in the first 2 hours of the day than in all others. Klaus, I understand you only have 2 office days left available for next month. Is that true?
Yeah, that is true. May will be an extreme heavy travel schedule.
Then you know what, we're truly fortunate to have you here. You know what, I'd like to just review the agenda a little bit. It's short. The topics will begin. I want to begin by introducing you to the RAIN organization and its mission. Afterward, I'll turn that over to Klaus to present a high-level overview of UHF basics, influences that affect frequency performance, and characteristics of long-range readers. That's a short agenda. So if I may, let's talk about this RAIN organization. RAIN is a global alliance of 136 companies promoting the universal adoption of UHF RFID technology. It's a marketing effort. Its goal is to simplify and promote the use of UHF RFID, much in the sense that of the NFC form or the
Smart Card Alliance.
Smart Card Alliance, so it's a brand. It takes those industry acronyms that we're all familiar with, you're all here, such as EPC or ISO, and industry terms like Class 1, Gen 2, and it places them under the umbrella of AIM. Feig Electronics was an early member of RAIN. I think we were actually number 4 or 5 to register as the organization. And we're a proud sponsor of this year's RAIN reception at the RFID Journal Live Conference. So at this point, if I can, Klaus, I'm going to give you the reins for now and give you a chance to start talking a little bit about UHF basics.
Okay, hi. Welcome to the webinar. And yes, we have a very nice international and big crowd here listening to us. And I want to repeat what Mike says. We want to make you aware about some technology pitfalls you can have in UHF or in RAIN technology. We are not here to finger point and to say this is better, this is worse or something like that, but we want to educate you a little bit if you have a project, where to watch out for and what to compare and what to do maybe. So just a little basic information means if you're looking to the worldwide frequency band from somewhere of 0 hertz here to even 1,000 gigahertz and everything else, and where all the navigation radios and everything is, where is RFID? And RFID is sitting here, or we're talking about, RFID is here in these 3 areas. So we have our low frequency worldwide, somewhere between 100 and 135 kilohertz. We have worldwide a uniform frequency for the HF band with 13.56 megahertz. But you see, there's a couple of red bars here which are presenting the area where passive UHF is, so from 860 to 960 worldwide. And then in the gigahertz range, there is where the active RFID band is located. One thing for physics to remember, this is an important line in the frequency band, because everything what happens below is technically called inductive coupling. So you have by a magnetic field, the energy transfer, and every frequency above that line pretty much is a backscatter coupling. So we have an electric field, energy is on an electric vector on that kind of frequency. So therefore, physically a totally different behavior. And that's quite important to consider in some projects. Little bit more to UHF. So our passive UHF band, you see here how we are spread out over the world now, with Japan on the higher end here, then China is really on the very low end. Europe is moving maybe here in the 920 megahertz. A lot of you guys are coming here out of the US or out of the FCC region. So here we have our FCC band and so on, just as a little reminder. I said I want to talk also about environmental influences. And in a lot of projects, people are not thinking about what can be between your antenna and your tag. And depending on the density of the material and the frequency you are using in your application, so you can have more or less influences. So here on the left side with that kind of an arrow here, I want to show something from plastic material up to water. And then here the frequency band, so our RFID frequency band. So in low frequency, you have almost 0 influences of increased density of materials. In the HF area, or in the near field UHF area, which also uses an inductive coupling, here you see we are getting to a little yellow if it gets to the higher density like water. So we get a couple of percentage influence, but on the higher frequency or the really high frequency area, so in our UHF band, so there we have significant influences until in water, so that we cannot penetrate a waterless body with our energy on an electric field. So a tag which is behind any kind of water kind, well, similar material will be invisible for us. Then what bothers us more in any kind of a UHF or a rain application? This is a picture with the beam emitted from an UHF antenna. But this antenna is mounted very, very high above ground, so you have no environmental influences. And then, yes, you see, like if the antenna would be here, so you have whatever your 3 dB, 5 dB, and whatever dB beam, very nice and very homogeneous coming out of the antenna. The right picture would be a view towards the antenna. So you see a nice circular with different kind of field strengths, energy fields in your antenna beam. But nobody can use an antenna on a high pole, maybe 40, 50 feet above ground. So if you are mounting your antenna down in your application, then it could look like this. So because now the environment is starting to reflect signals, and you get something like fingers here. So you see, like you are reaching, even if you compare it to the picture above, you are reaching even far further out with some kind of areas, but you are also losing in some areas where you had here theoretically a very nice field. So you have certainly in certain areas no field anymore. Yes, and this picture here, so the front view to that shows that means, so if you would move horizontally in front of an antenna with your tag, you read it. In the black area, you read it definitely not. In the gray area, depending on sensitivity, you read it not, you read it again.
Klaus, can I ask a question?
Yeah, sure.
Can those reflections be predicted or controlled in any way?
No, means there's even no theoretical model. I promise you, if you move that antenna even by 3 feet in that same room, you will see a complete different picture in that moment. So
what can you do to overcome it?
Important is that you are designing a system, you see, like that you are, it means if that is the end of your maximum read range, for example, so to get 99% of your tags, you should not design your application that you are operating in this area, because then you are operating in this crazy area with reading and not reading points. Yes. So if you put your application, or if you're operating your application in a more safe area, and then also the other trick, or not trick, is to add antennas to your field, so to attack your kind of reading area with multiple antennas, so that these kind of fingers or reading holes are more overlapping, so you get your coverage you want.
Oh, thank you.
You're welcome. It's just a little bit of a different kind of display of that kind of area. That means like this would be like your reading beam of an antenna in an undisturbed area, but then in real life, so you will get like islands of reading outside, so even much, much further away, and you get reading holes inside the area where you are theoretically expecting to read your tag all the time. Means so you are losing tags in your predicted area, and you are gaining tags which can be quite far away, which you even don't want to read. So that's always to be considered in a system operating in the ultra frequency range, ultra high frequency range. So that's enough about environment. Means most of you, as I'm sure, are very, very familiar with that kind of influences of a UHF system and have enough experience to design something in that area. So, but here is even means one of the RAIN groups, the RAIN working groups, that is, I think last year was it. So they are some studies and some discoveries were really surprising for a lot of experts of us. And what was done? So we're taking two tags or two inlays. So you're taking a tag which has whatever sensitivity, and then you are taking a tag which is just 2 dB more sensitive. And 2 dB more sensitive is typically an indication this is a more modern design, because if you are looking back over the last 10 years, you see almost frequently that tags entered the market each year which got 1 dB more in sensitivity for year and year. It says maybe a year not, but then a year with 2 dB and so on. And normally that's a great thing, because even the newer tag has not only a higher sensitivity, the newer tag quite often comes also with an incentive. You get it a little bit cheaper on the market. So, and if you now put this kind of tag on a test, so, and for the test we are taking, let's say, a common on the market modern fixed reader, or we are calling it a long range reader, which are somewhere in the area of 83 dB sensitivity.
Okay.
And now you are throwing your two tags, or you are throwing a lot of tags in the field and measuring what's happening. So let's say your older tag is getting like a performance line from that. That means here it was a test done with 100 tags. In this vertical line, you see the reading percentage of that kind of tags. And on the bottom line here, the increased power in dB of the reader. So increasing on each square here the power by 2 dBs, and then you see how much percentage you are getting more. So you are throwing the new tag in the game, and yes, you get exactly what you want to see. A more sensitive tag, so you get a better reading performance, so your game is done.
And at a lower cost.
And at a lower cost. But now there are maybe some installed applications already where you are using, let's say, a generation or 2 generation older fixed reader, or what we see today, even still today, a lot of handheld readers. A lot of handheld readers are having quite a lower input sensitivity as the today's fixed readers. So let's say we are choosing a reader with a sensitivity of 65 dB. And if we are now throwing the 2 tags in the game again, with this first tag, our older tag, so it happens, means it looks exactly what we are predicting, because we have a less sensitive reader. So we are dropping down on the same power level. If you put the end of the blue line down here, so we are dropping down that we are getting approximately 15% less of the tags in our setup. Quite normal. And if we are now throwing the new tags in, the higher sensitivity tags, so everybody, means everybody was asked before this was presented, everybody, even really a lot of experts in the room, and said, yeah, we are getting something parallel to the old test. Yes, but I will surprise you. This is really what happened. Yeah, and we can make a webinar about 2 hours to try to explain that kind of details. But the details why it happens has something to do with the backscatter function of the tag itself, and then the sensitivity on the input is now blocking out, or is in that moment almost blocking out certain kind of tag information coming back, that you are losing tags. It means you have a higher sensitivity tag, and you are losing dramatically on read range.
That's a disaster waiting to happen.
Yes, means like, especially if you think about, you have a customer and the customer has an installed park, and you are responsible supplying tags, and you are maybe happy and very proud that you found cheaper tags and even higher sensitive tags. So you say, hey, you are getting for less money more performance. But if the customer has now really lower sensitivity readers in his park or in his installation, you can have a dramatic bad experience. That means this does not happen quite often, or not very often, but it definitely can happen, and we just want to make you aware that to watch out for it if you are changing tags, especially if you are changing sensitivity of tags. Verify what kind of readers you have in the field, and if you are not sure, run a test before you are ordering 1 million tags.
Yeah. Good advice.
Yeah.
I could imagine, companies buying millions of tags, more sensitive, lower cost.
Yes.
Boy, but they go to deploy them and then it looks like the reader's broken.
Yeah, means like even it's a lot of people who saw this the first time didn't believe it at all. And I'm sure a lot of guys sitting with us in that solution group of RAIN have verified that test at home. Okay.
Let me go back and talk a little bit about the RAIN again and RAIN itself and reader and system performance. I mentioned RAIN's mission is one of marketing. It's one of education to make RFID simple. And we pulled this information right off the RAIN website. Look, low-cost solutions to identification and no batteries, they last forever. Read ranges, over 10 meters or more, 1,000 tags per second. Now we see sensor technology coming, both moisture sensor, temperature sensing, coming on board a RAIN tag. And with the Gen 2 V2 standard, then encryption capabilities, security features that were totally lacking previously are now available to improve sensitive applications such as anti-counterfeiting, for instance, or even access control or vehicle road tolling applications. So,
yeah, this is exactly correct, Mike. And I picked this kind of slide. This is an original slide from a RAIN presentation, and there's nothing wrong on this slide because these kind of buzzwords are used all over the internet. It means you can read how many tags can you read, and you'll find everywhere statements somewhere between 700, 800, 1,000 per second.
Yeah.
Because theoretically it's possible. And we had quite a lot of customers with high speed, high volume applications. So, and we put our readers to the test and we're a little bit surprised what we have seen. And therefore we took the decision, hey, let's put a couple of more readers to the test and see what kind of a performance is the industry getting and not only we are getting.
Okay.
So what we did, we went out and bought a few readers. We didn't have to pay for our own one. We had it in-house, but we bought the Motorola, 2 Motorola readers, means like now Zebra. We bought a Speedway and a Pinch reader, and we bought from Europe a Catrine reader and put these readers to the test. I want to show one little bit more remark to our fixed reader, because we have not one fixed reader. They all are sitting in the same housing, but with a quite different kind of hardware and some other performances. So we have these kind of 3 long-range readers. Means like whatever we are using, we're calling the basic model, and then an improved one, and really a high-end model. Here, just a few parameters, which I don't even want to read, how they are differentiating. But because they are differentiating in performance, they differentiate in price quite significant. That means like this reader, so that mid-unit or mid-range reader here in that area is already 66% more expensive as our basic model, that LRU 1002, because that model I want to name because we're using that a couple of times more. And the high-end reader here is even 135%, so significant more expensive. For our test, which did we choose? I think everybody expects the far right one. No.
Okay.
We use this model because the reason is because that model is exactly commercially in the same ballpark as all the other readers I showed on that slide.
Okay.
Yes, now because depending what kind of quantities you are buying as a customer, and everybody knows with higher quantities you get lower prices. But whatever we have, what we know, this is the competitive model to the mainstream market. So we used it for our tests. So now we are running the first test, and I think I have to explain a little bit. First, I have to apologize because I used all the sheets and charts from our development guys, and you know where they're sitting in Germany, and guess what the decimal point is in Germany? It's not a decimal point, it's a comma. So, so therefore, the point, comma, 410 is a 0.41 seconds, so it's 410 milliseconds here in that case. You see that all over the slide. So the first test we're running, and something you maybe also see, yes, we are naming our reader here as number 1, not because we are number 1, and then we are just giving our competition the names A, B, C, D. We're not changing the sequence, but as like we definitely we are not here to finger point on anybody. We just want to show, because at the end you will see there are a lot of common problems we all have and customers should be aware of.
Oh wait, before you go on there, you know, you take 100 different transponders and the average speed is, that doesn't equate to 1,000 tags per second.
No, quite not. The next slide is getting a little bit an easier comparison. Here in the first test, we just say, look, from the best to the worst model, there is a difference of 259%. So it means this bites you only if you are doing a very, very fast application. If you have to accomplish a very fast application and would compare just these two readers to each other, then you see, like with the last reader with number D, you can really run, if speed is an issue, in quite some bottlenecks in that application.
But not all applications require
the
fastest speed. I could think some applications require, you know, racing applications, you know, road tolling applications where you're, you know, traveling hundreds of, you know, kilometers a second perhaps, and that's important.
That is exactly. Let's see, a few percentages of applications are very, very speed sensitive. Yes, and then I think it's very, very important that you have maybe running your own tests with your own transponder in the right environment to verify that your speed requirements are met by the hardware you have chosen for that application.
But it's effective to show that, you know, across the industry there's variances.
Yes. Now you see, like we have in this comparison, I would say almost means like here 2 readers ours and 1 reader here, which is even slightly better, as in that case as our ones now are pretty much, I think, but you see, like nobody is significantly better. 2 are at the same point, 2 then are a little bit at 50 and 100% slower. 1 is a little bit really out of the picture. But I think these numbers are a little bit easier to read now. Because we wanted to do a second test. Because also we had indications where we got approached where people told us, I'm getting different results depending how many antennas I'm using in my application. And sometimes to the good and sometimes to the bad. So, and therefore we put the test up again, and now we said, hey, we are making up a 1 second window, and then we are running in this 1 second window, so a large amount of tags, and doing this kind of test by running just 1 antenna, 2 antennas, 3 antennas, or 4 antennas. Because, yeah, Mike?
So like a portal application.
Exactly. Now, very, very typical for a portal application. And you see even, because that is very typical, because all 5 readers we have chosen for our test, all of them have 4 antenna ports.
Okay.
So it's to have 4 antenna ports is a very, very common thing for a fixed or a long-range reader for that kind of applications. Now, what we see here now was even a little bit surprising on some areas. If I'm looking, so if we are looking, whatever, look for each reader on the horizontal bar, and let's make it a little bit easier. So you see our reader has 3 and the second reader has only 3% variation in the amount, how many tags you can read per second. Also one explanation, you see here decimals in, because we did not run it 1 time, we did run this test 10 times and averaged from each run exactly the tag numbers. So therefore, in some averages, you see then a decimal point in red tags, just to be accurate. Here, you will see means like, I consider here 3 readers as being not influenced by really the multiplexing task they have to do. So that means they are doing, what does that mean? So they are doing their internal antenna switching pretty fast and obviously without any kind of noise production. Yes, because if you are switching and producing noise, you are overpowering your input amplifier. So therefore you are losing time until that amplifier is calming down almost in a way. One reader here, in this case number 2, you see, I think has a huge problem. That means here you are dropping from 131 tags on one antenna, which is already not the best result, to 95 tags almost. So a drop by 40%.
Okay. But you know what? Not all portal applications require high tag volumes. For instance, a tool crib. You pick up an item, you walk through, you just have maybe a few tags. That would be acceptable. You know, that's still performing in an acceptable level. But maybe it's different if you have a portal that has maybe a pallet load of goods going through, where you're trying to catch hundreds of tags.
Yeah, that is not an easy answer. I can answer it. You are right and you are wrong. In a way, you are right, yes, because if you are looking, if your limit is, let's say, at 95 tags you need to read per second, you can use every reader you have and you will get your achievement done, depending what setup you have. But if you have a portal application, and quite often, maybe as a system integrator, you are making your homework at home and try to test and to stop the time. How long does this reader take to read my 100 or 200 tags, which can be on a pallet? And I have a pretty fast forklift driver in this warehouse. So you are running your test maybe on one antenna, because it's in the office much easier to set one antenna up as 4 antennas up. So, and you are reading, even with this reader, securely 130 tags, you say, okay, we are fine. But then the installation happens and you are dropping down to 95. And now the chance gets very high if you have 200 tags on a pallet and your forklift driver is a little bit with his foot too much on the pedal, on the accelerator, so that you are missing tags. And you have, again, you tested maybe this column and said, I can read securely 130 tags per second. Yeah, because you are getting a surprise, because multiplexing can have significant influences, but you see it doesn't must have, no? Because I would consider here at least 3 or almost 4 readers. 10% is a little bit high, but I would still consider that's a good number. It means that's a typical number for a little bit of noise coming after the switching. In overall performance, yes, you see even there is a significant number. Between our worst result and the best result, we are looking on a difference on 178%. But you see 1,000 tags, what the industry says. So where are the 1,000 tags? And I think we are far away from 1,000 tags. It means to this test, a lot of people will tell us, no, we can show you, we can read 600 or 700 tags with our reader. And I say, yes, but what are you doing to do that? You are configuring the reader first in a mode which violates typically FCC, because you're putting dense reader mode off, you're putting the reader only on a locked channel, and you can do some other tricks to increase your tag number. But dense reader mode is, for example, it's required because I think you are not interested to read in your EMV protected chamber 500 or 800 tags and be happy about it. I think you want to read it in the field.
It's kind of like a speed shop, a motor speed shop. You could pop up the hood and soup up the car, but it wouldn't be street legal.
That is 100% correct.
Okay.
No, but you see the other number, therefore it's interesting. So again, and I think all these kind of readers will have, or manufacturers have certain kind of tricks, what I can do to increase that kind of tags per second. But I say, like, that is not the true story. In this case, the readers, all readers have been honestly configured to radio regulations and field conditions, so with dense reader mode on and all that kind of stuff. But then you see, like here we are running in the range of 250 tags in that area, 240, 250 tags here, the light green and the dark green ones, which is a realistic number you can achieve in the field. So if you design an application where you say, hey, if I read 200 per second, I'm safe, my application will work, then I think you have enough margin for a little bit of noise or any kind of influences that your customer is not screaming about at you. Okay, that is my remark, a little bit to the point of speed. Then we did one more interesting test. So we wanted to see what is the sensitivity of the reader. Means that is something I personally get asked every time. A customer calls me and asks me, your data sheet is not showing the sensitivity. And there's an easy reason for it. Sensitivity or reader sensitivity is not a value which is easy to determine. So you have to do a couple of measurements and calculations to figure it out. And the terminology or the methodology, how to do it, is not standardized on the market. So therefore, if you would take the data sheets of all 5 readers here, you will read most likely different sensitivity values as we have written them down here in that area. So, but we took all 5 readers, we put it in an EMV chamber in the setup we think sensitivity should be determined. And we measured, and you see 3 of that readers are coming out exactly with the same value. Mm-hmm. One is just a little bit below, one is really below. So this guy has really some problems with the input amplifier or sensitivity. But if this number now is 82 or 84, depending how you are calculating, or 81, it doesn't matter. But important is to see what is the difference between the reader models here. Yes, and here's a very nice picture. That means 3 of the readers on the market are pretty identical in sensitivity. But now, where did we measure that? And where did I tell you we measured that? We put that in an EMV chamber. So a very expensive piece of measuring room where you have 100% no electrical noise inside, no electrical waves inside, and nothing.
It was better this way because at least you're everybody's doing it in the same fashion. You're not just taking a data sheet and assuming that the test was done the same.
Yes, and you see, like at least I would say almost 4 readers on the market have, I would say, goal achieved. They have a very nice sensitivity. But now what happens if we are going to real life?
What do you mean by real life?
Real life means I will put this reader out of the chamber and I will put it in, for example, let's say in a warehouse, and I will put it on a dock door. And if I do that, I know a typical distribution center or logistics center has not one dock door. They had a couple of dock doors. So there will more readers operating in that kind of environment. There will be more readers being active. So, and therefore, so we now activated, we put the readers up, and we put now a second reader, and that reader we put manually, to transmit in the neighboring channel of the first reader. And what happens now to the first reader? What means it in the neighboring channel? It means the frequency regulations and the bandwidth are quite different in Europe and the US. But you can this kind of findings you can see exactly if you are doing the measurements in accordance to FCC rules or European rules. So there's pretty much no difference. Yes, there's pretty much no difference. And for me, very, very disturbing was already if I see our reader is losing in that moment 4 dB sensitivity. And 4 dB is a big number normally. Because 3 dB means normally half the signal. But it's on the sensitivity side, it's not as dramatic, because on the sensitivity side, we are just looking to the tag answer in that case. But if I see that other readers in that case are losing 24 dBs, which I think is absolutely dramatic. Yes. No, and I think that is something you see you will never figure out if you are running your test in your office
with one reader,
because you have typically one reader exactly running. And I think what's even worse on this kind of scenario is, so if the readers are hopping far apart on the channels, so they are maybe working close on this kind of original measured sensitivity here in that area. But now suddenly the next doctor, the reader hops on the neighboring channel, and you are losing performance like hell with certain kind of readers. So the customer, you are the integrator, the customer calls you, is complaining about the system. You are sending your technician out, and sure, the reader is back on an, or no neighboring channel is occupied in the moment, and everything works fine. Yes?
Well, this says two things to me. Could be a cause why nobody's getting 1,000 tags per second, when you're getting conflicts and channel blocks. But what other issues does it have on affecting performance? Then you're losing distance, reading range?
Yes, you are losing, means like you cannot, this dB here, you are losing here on sensitivity, you cannot correlate that in an easy chart in a loss of performance. I may be using, or first is like one number more here, means like between in that moment the best and the worst one, again we have a drop of 28 dB, which is really catastrophic. That means here you are losing, I guarantee you, more than 50% of your previous read range, and I would even guess it's more than 50% what you are losing. How much you are really losing is very hard to calculate again, but if I use just this chart we have used before, how much you are losing, you can see a little bit in your chart. It means like if you operate your reader, let's say in this kind of an area, and you are losing sensitivity, you see like the increase, so that with the increase of power or increase even in sensitivity, you have a steep increase in read performance. So therefore, if you are decreasing here a little bit in that kind of an area, you have immediately a dramatic drop on performance. If you're operating a reader in this kind of an area, so where you have a much smaller slope, I would guarantee you, if you are operating your reader in this area and you have a 4 dB drop in sensitivity, not in power, then you cannot even recognize that kind of loss. But 28 dB you will lose definitely here. There's no question about that. Yes.
You know what I noticed with you? It's all about building in margin.
Yes, that's the point. Means like never engineer a system at 90% performance or 90% point, because then you are losing 5 or 6% and you are toasted. But what is the result? Means like this is for me also the surprising part. You see, like I just put all our tests, our speed test, our anti-collision and multiplexing tests here with a different kind of, so different numbers of antennas, and the dense reader mode test with sensitivity. But you see that it's not one of the 5 readers which has the dark green from the beginning to the end. Yes, and that means like one reader is obviously really less performing as the others, but if you are taking the other 4 readers, you see this one has green or dark green here, and all in this area, this one has dark green here, this one has dark green here and light green here. But what it shows means like, I think the dangerous areas are really red and even orange. So depending on your application, what is the challenge of your application? Is it more the dense reader mode? Is it more the speed? Is it more the sensitivity? Is it the multiplexing of more antennas? So I can only encourage everybody on the market, test your chosen reader exactly with the challenges of your application, because that is the only way, or that is the only chance you can avoid surprises you will not like. Yeah, and that means it's from my side, and I think, Mike, we are opening. Means here is a preview, or means this is the white paper we wrote in accordance to our presentation. So we are summarizing the findings a little bit, and you can download it after, I think, the webinar.
Yeah, you know what, this webinar will probably take a few days till we get the recording posted up.
Okay.
And I do promise to the attendees, we'll send out a link to that YouTube and also a link over to this download for the paper as well.
And I promise you guys, I will not hide. So next month, you will find me from May 9 to 11 in Phoenix on the RFID Journal Live. And a week later, from the 15 to 17, UITP, that is about payment and public transport, a worldwide show in Montreal. So whoever our friends from Canada being in this meeting, or whoever is even involved in public transport or payment systems is maybe attending the UITP show, I will be there too, and I'm very, very open to discuss any kind of questions.
Okay. Let me just open up your questions file. I don't know if we have an issue seeing the questions, but I don't see any questions posted.
It can have two reasons. I was too confusing, or I was too clear.
Maybe. So, I don't know. Kelly Stark, you're on the call with us today. Kelly is our marketing services provider for Feig Electronics. Kelly, do you notice any questions over on your side?
Yes. We have a question here saying, we are seeing readers being manufactured with over 30 antennas built into them. On a spec sheet, they look nice, but what challenges do they present in the real world? Is this something Feig would even consider?
I will take that question, yes. Means like we are not producing a reader with 30 antennas. The reason is because the applications where something like that would be needed is so rare. That means either way you are making that reader so cheap and flimsy that the performance is already bad, or you are not making any money out of it. We are doing a compromise. Means like, first, if you're adding, the more antennas you are adding to your system, the slower you will get in getting around, and it all depends on your tag population. If you need 30 antennas to read maybe 1,000 tags, you should be aware it will take you maybe 5 seconds or 4 seconds to get your 1,000 tags, but it's possible. We are solving that problem. And so like we did not do a product presentation here, we are calling it external multiplexers. So you can hook up to one output channel of our reader, an 8-channel multiplexer, and you are getting, so from one antenna, 8 antennas. And it's even very weird. So you can put a multiplexer at the output of a multiplexer again, and a multiplexer and the output of the next multiplexer. So you can cascade it up to 3 levels. So we can operate on one antenna channel theoretically up to 512 antennas. The switching is not an issue, because you see, like switching, we are switching as fast as in our reader, the antennas, and we have even measured it. We are switching channels below 1 milliseconds. But the problem is UHF signals, everybody knows about cable losses. So if I have so many antennas, I have to most likely get very, very long cable runs. So this is introducing very high losses. And the multiplexer itself also adds a 2 dB loss in your chain to the antennas. But as like, if you can afford it, you say, I have the time, I want to cover even, let's say like, I want to make something like a real-time location system for a staging area in a warehouse, and using maybe 30 or 40 or even 50 antennas, and so like, and I don't care if it takes 2 seconds or 6 seconds, then you can do it.
All right, we have some more questions. Many read points have the additional need of sensors. Can you explain how sensors integrate with your readers, and what are the GPIO options?
Sensors have typically one problem. the nice part on sensors is using, so they are using, all of them are using the Gen 2 air protocol. So that means that the basic communication is there, but pretty much every sensor I have seen has a proprietary command set to get to the sensor data and the approach. So, and that means in a standard configuration that your reader must have a special firmware to support that sensor. Even there we have I think it's a very smart solution. We are calling it, we have a transparent command mode on our reader. And a transparent command mode is you can send a container from your application to the reader, so labeled as a transparent command, and then the reader says, okay, my firmware is not trying to check anything what you are sending me. I'm taking this bit pattern and sending it as an API to the tag, and I'm putting the tag answer back in your transparent command container and giving you the information back, and you have to live with it. We cannot give you error messages. But therefore, you can, every tag on the market, every sensor tag on the market works, therefore, or let's say 99% will work with our readers immediately.
Kelly, that question itself, did you say something about GPIO as well?
I did, yes. And Anthony's explaining a little bit more. He said the sensors he's typically talking about are the ones tied into the reader that include like light stacks and IR beam sensors, motion sensors. So for instance, to power up or ID direction, things of that type of sensor.
Yeah, but it's like that kind of sensor technology is not a problem to
as an input to the reader, maybe it's triggering the reader to go into.
Also, that point means yes. First, so like first you can trigger. We have digital inputs to trigger certain kind of events on our reader. We would even have, that means like the two higher end long range readers have even a Linux operating system on board. That means even there you can write with a SDK an own application and could even read a sensor via a serial port on the reader or via the USB port on the reader, and preparing any kind of data you are using to send to the host system or to do or initiate any kind of reactions from the reader itself.
I can imagine too on that type of question that certainly you could use an input on the reader to basically keep the power level of the reader off until you see a sensor input, then you turn the reader on, and then you maybe avoid some of this collision issues that are happening.
Yes, but you see, like the more sensitive you are maybe to readers in dense reader mode, the more often you have to do this. And if you are less sensitive to this kind of stuff, you can even save maybe money in your application by neglecting that kind of point. Yeah. Because the power consumption by itself is insignificant. That means if you are going green, and want to save the electricity of 5 cents a month or something, yes, you can do it. But I think most triggered kind of applications are done to avoid more interference between the system, or what we have shown the dramatic influences on a couple of readers under dense reader mode.
Yeah.
Well, I'll let you follow up with him. He was regarding, dock door type of environments and those kind of, things where you might want some sensors. So I'll let you follow up with him. There's another interesting question. It says, what is your sense of when the quote, be in, be out will be the mainstream on transit given your expertise?
Bluetooth in, Bluetooth out on a.
Oh, that's what it meant. Yes.
Bluetooth in, Bluetooth out for on a, for instance, a transit bus. So they get a sense of when the person comes on board, and then when they go off the bus.
But so like that, tracking people with UHF will have this challenge. Think about the influence of water. Yes, and humans are 98 or 99% water. So a tag hidden by any body part between any body part between your tag and an antenna means you are not readable in that moment. Yes, for UHF. And I think therefore for tracking people in environments where you have also that kind of dense not reader dense people mode, like on a public transport system, I think this kind of frequency would be the wrong way or the wrong approach trying to track people.
I actually had a conversation with the founder of the company that was doing all the measurement for the cell phone towers around the country. I think he sold the company for $250 million. And I approached him on B in and B out on this application. And he pointed out to me that, you know, use of Wi-Fi, more people are using Wi-Fi on their phones than the Bluetooth. And he said, and we were in a restaurant, and he indicated to me, boy, I can see, okay, a couple Bluetooth devices. But he said, I'll tell you right now, if I, was looking for people that had their Wi-Fi turned on, I'd see 90% of the people in the restaurant. So maybe it's a hybrid, Bluetooth in, Bluetooth out, in addition to using maybe Wi-Fi.
Yeah.
All right. Next question is, I think the intent of the multitude of antennas is to simulate real-time locationing. Does Feig feel that UHF is a viable platform for RTLS type applications?
We don't believe in that directly. It's like if you are, because people are expecting typically too much. People are expecting typically something better than a foot or something like that in that area. And with passive RFID, you will not achieve that kind of a point, because whatever people are theorizing about phase measurement and RSSI values and everything else, whoever has tried it, measure the same tag with two antennas out of two positions with the same kind of distance, and you are getting surprisingly very, very, very different kind of values back. If you are doing it on a bigger grid, now I have seen an application where a customer really did it just in a staging area for dock doors, because they had the problem that pallets were placed at the wrong dock door, and then not loaded. So on the pallet level and having a grid, hey, it's here in this dock door area plus minus one other dock door area. Yes, that you can do. Enough antennas up. And so time is not an issue, and reading, just filtering and reading tags only on pallet level, not item level, I think then it can be done.
Okay, last question here. Do these readers operate on the LLRP protocol?
Yes and no. We have even their very special solution. Everybody who uses LLRP knows about a little bit of the bottlenecks and the restrictions of LLRP. And then what we didn't like is that LLRP is typically only on high-end fixed readers possible. And a lot of applications are calling for readers with lower power modes and even want to have LLRP. So we did, you can call it a wrapper. So we did a piece of software you install next to your application on your server or on your PC, and you talk to that wrapper via LLRP commands from your application, and that DLL, what it is technically, then talks to our readers, and now you have access of 5 or 6 different kind of UHF reader models, even in the very low price range for shorter applications. And we are talking then our Feig proprietary protocol on that side. So everything is open, everything works with LLRP, but it's not a direct connection, which normally doesn't matter at all. Even gives more flexibility.
All right. Well, I kind of told everybody else that we'll kind of follow up after this meeting with other questions. And as we mentioned, we can have this presentation and recording as well as a white paper by Monday.
Yeah, and that's you see I put a very easy email address up, the sales@feig.us. Who is not expecting to see me either way in Phoenix or in Montreal, so send us questions if something comes to your mind today, tomorrow, whenever. And talk to us about your applications, and we are more than happy to help you.
Okay, wonderful. Thanks again, everyone. You know what? Over in Asia, go back to bed. Over in Europe, go to bed.
Yes.
And we're going to finish up our day. So thanks, everyone.
Thank you.